Okay, so let's go ahead and get started. So today, what we're going to do is we're going to continue on with where we left off with conservation of momentum and collisions, and then we're going to continue with some new material, which is going to be over circular motion. But just to remind you, our equations for momentum conservation. So we define the momentum to be is a vector, which is going to be the product of the mass and the velocity vector. Now, in situations where we say that the momentum is conserved, what we say is that the sum of the momentum in the initial state is equal to the sum of the momentum in the final state. Now, there were two types of collisions that we talked about when we conserved momentum. The first was the inelastic collision, so the inelastic collision. In this case, momentum is conserved, but energy is not conserved. So P is conserved, but E is not. And we also had the elastic collision, the perfectly elastic collision, in which case the momentum and energy are conserved, so P and E are conserved. So last time we left off with this problem, and I kind of rushed through the answer to it, so I want to give you some more time to work on it, where we had this ballistic pendulum. And so what ended up happening here was we said we had this bullet with some mass lowercase m coming in and striking this block of mass capital M, and then they move up together. And what we'd like to do is we'd like to use this apparatus to be able to determine what the initial velocity of the bullet was. So go ahead and take, we'll say maybe about 10 minutes to work on this one again, and then we'll come back and talk about it. So let's go ahead and talk about this one. So what I have here is I have these three states, A, B, and C, drawn here. And what we're trying to do is we're trying to set up an equation that can allow us to solve for what this initial velocity is, because we're given everything else. So in order to do that, what I need to do is I need to connect the state A to the state B, and connect the state B to the state C. Now, between state A and state B, we know that momentum is going to be conserved. And so what that says is that the momentum in state A is going to be equal to the momentum in state B. And in general, these are vectors, but this is happening only in one dimension here. So what this says is that m times v0, where lowercase m is the mass of the bullet, is going to be equal to the sum of the masses, so m plus capital M, times the velocity that these are going to move off at the instant after the collision. And this is what I'm calling v1. So this is one equation. This equation connects state A to state B. Now, the next equation that we can get relates state B to state C. And between state B and state C, we can say that energy is conserved. And so what we can do is we can write down the kinetic energy in state B, which is going to be 1/2 m plus m times v1 squared. And this is going to be equal to the potential energy in state C, which is going to be m plus m times g times h. Okay, and now we can cancel these masses. And what we'd like to do from this equation is solve for what the velocity is, because what we really know is what the height is, and we're trying to get from this height back to this velocity, this initial velocity, mv0. And so from this equation, what we can do is we can rearrange this to solve for this velocity v1. We end up seeing that v1 is going to be equal to the square root of 2gh. Now, in this equation, we're trying to solve for what v0 is, so we can move a mass over to this side. So we have V0 is going to be equal to m plus m divided by m times this velocity v1, but we know what that is now. And so we can take this and we can plug in this root 2gh, and then this is our expression for this initial velocity. Now if you take the numbers that we have here and convert them to SI and evaluate, we end up finding that this is going to be equal to 284 meters per second. Okay? Any questions about this one? All right, so let's move on to the next one. So the next one says, at an amusement park, you were trying to win a prize by throwing a ball and knocking over a bottle. You throw a 2-kilogram ball at 1 meter per second towards the bottle, which is about 1.5 kilograms. Assume this is a perfectly elastic collision, or perfectly bouncy. We want to calculate the final velocities of both the ball and the bottle, and we want to think in the process of doing this, what type of collision is this? How would we, how will the pre and post collision kinetic energies compare? And then this is seemingly not a working hold question. So just do this and then we'll talk about it. There's no clicker portion for it. Okay, so let's go ahead and talk about this one. So I have drawn here the initial state where this is before the ball hits the bottle, and then the final state I haven't quite drawn in yet because we want to look at what the problem's telling us in order to do this. So in the problem it says that the ball has a mass of 2 kilograms and the bottle has a mass of 1.5 kilograms. We also know that this is an elastic collision, and so when these things hit, they're going to bounce. So the question is, when this ball hits this bottle, how is it going to bounce? Is it going to bounce this bottle forward, or is it going to bounce backwards off of it? Well, the answer to that has to do with the relative masses of these things. And so the ball is more massive than the bottle, because the ball has a mass of 2 kilograms. The bottle has a mass of 1.5 kilograms. So when this hits, it's actually going to keep going in the same direction. So this is going to be m, and this is m, and we can call this some v1, and this is some v2, okay? Now, because this is an elastic collision, we know that both momentum and energy are going to be conserved. And so what that says is that P, sum of P initial is equal to sum of P final. And so my momentum in the initial state is going to be mv0. This is going to be equal to mv1 plus mv2. And we can also say that because it's an elastic collision, energy is conserved. So E1 is equal to E2. This is going to be 1/2 mv1 squared plus, or mv0 squared, is going to be equal to 1/2 mv1 squared. And these should be different masses. I need to call this my capital M. So that's going to be capital M plus 1/2 capital M v2 squared. Now we can cancel our masses, or sorry, our 1/2s here. And we have an equation that's kind of tricky to solve when we look at it, because we have this mv0 is equal to mv1 plus capital mv2, and this mv0 squared is going to be equal to mv1 squared plus mv2 squared. Okay. So what we can do with this, and I'm not going to go through the whole process of solving this because it is a little bit labor intensive. We can take one of these equations and we can either square this one and then plug it into this one, or we could take a square root, manipulate this one and take a square root and plug it into that one in order to solve this. Okay. Any questions about this? the most important thing, and the thing that we're really testing over here, is your ability to set up these equations. In a case like this gives you an equation that's difficult to solve, and so we're really more interested in, can you identify the physics and set the equation up properly? Okay. I don't have the number for that. I had it written down, and I don't have the piece of paper, but I can look it up. Okay, any other questions? All right, moving on. So this is another problem where I'm not going to ask you to do the numbers for it because it does end up being a little bit tedious. But what I want you to do is I want you to set up the equations for this. And what I want you to see is how these equations are going to manifest themselves in 2 dimensions now. So in this situation, we have these 3 balls that are going to be moving together, and they're going to stick. And then they're going to move off afterwards. But the thing that makes this one a little bit more challenging than the last ones is the fact that this is a collision in 2 dimensions instead of a collision in 1 dimension. Okay? So take some time and work on that, and then we'll come back and talk about it. So let's talk about this one. So this one really follows in spirit from the things that we've been doing so far. The only difference here really is the fact that now instead of conserving momentum in 1 dimension, we're conserving momentum in 2 dimensions. And so in order to do that, what we need to do is we want to write the sum of the momentum in the initial state in x is going to be equal to the sum of the momentum in the final state in x, and the sum of the momentum in the initial state in y is going to be equal to the sum of the final momentum in y. Okay? So now that we have these equations, it's helpful to draw some coordinate system here. So we can define what the x direction and the y direction are. And let's label these velocities. So call this one some velocity VA, call this some VB, call this some VC. And each one of these have the same mass, just m. Okay? So let's write down what the initial momentum in x is going to be. This is going to say that this is going to be this mass times the velocity in a, so mVA, minus the x component of this momentum, which is going to be m times VC times cosine of this angle. Now the angle that they give us is 150 degrees. That means that this is going to be 30 degrees because it's really giving you that angle or that angle. Okay, but this is 30 degrees as I have it written here. Now this is going to be equal to the momentum in x in the final state. And so the momentum in x in the final state is just going to be the sum of the masses, because these are all going to stick together, times that velocity in x. So this is going to be 3m times vfx. Okay? Now we want to do the same thing in y. So when we do the same thing in y, we end up seeing that this mass here, mass b, times the velocity in b, plus the component of this momentum that's going to go in the y direction, which is going to be mvc times sine of theta, is going to be equal to the total mass, which is going to be 3m, times the final velocity in y. Okay? Now, if we had wanted to solve this, what we could do is we could say, we know everything in this equation except for the final velocity in x, and we know everything in this equation except for the final velocity in y. We just need to rearrange this to solve for that and then just evaluate for the numbers that we have. Now, the other thing that it asked us to do was to compare what the initial energy was to the final energy, find a difference in kinetic energy. So in order to do that, what we can do is we can just write down term by term what the kinetic energy is going to be in the initial state and in the final state. So in the final state, the kinetic energy is going to be 1/2 m well, it's really 1/2 times 3m, right, because we have all three of these masses, times the final velocity squared, where this Vf squared is just going to be equal to Vfx squared plus Vfy squared. And this is going to be subtracted from, this is the final kinetic energy, so we want to subtract the initial kinetic energy, which is just the 1/2 mVa squared plus 1/2 mVb squared plus 1/2 mVc squared. So this is going to be 1/2 mVa squared plus 1/2 mVb squared plus 1/2 mVc squared. Okay? So were we to do this calculation, what we would end up finding is that this would be a negative number. So this is less than 0. Okay? Now if it was identically equal to 0, we would say that the energy was conserved. But we know that energy is not conserved because this is not a perfectly elastic collision. So this has to be less than 0, which tells us that there's some energy lost when these collide and stick together. Okay? Any questions about this one? Yeah.
So for part A, since you don't have just a numerical value for m, you just...
So you don't have numerical value for m. That's okay. Because when I look at this equation, all my m's cancel. Yeah, so set it up as if, and this is in some way the virtue of doing these things algebraically, because sometimes if you're kind of fixated on having numbers for everything you think you need in the equation, then you run afoul because you're like, well, I don't have the mass, right? But if you set this up like this, you realize you might not actually need it. Yeah, okay. Other questions? Okay, so let's move on to the next one. So the next one, so we just did a perfectly, this one was a perfectly inelastic collision. Now we're going to be doing a perfectly elastic collision. So in this case, we have some mass of m, lowercase m, moving to the right with some unknown velocity. This is going to come in and hit another mass, and then these are going to scatter so that one of them is going to be moving above the x-axis with some angle phi. One's going to be moving below the x-axis with an angle theta. And what we want to do is we want to set up a system of equations that we can solve for the masses. Okay, so just to give you a diagram of what's happening here, this is the mass m. It's coming in and hitting this big mass, capital M. And then afterwards, this one's going to go off like this. This one's going to go off like this. Let me just make sure I do it exactly the way that I wrote it. Okay, yep. So this is going to go off at this angle phi. This one's going to go off at this angle theta. Okay? And these are all unknown velocities that we have here. So call us V1, V2, V3, and then the angles are known. And so what we just want to do is to set up a system of equations that we can solve. Again, not intending to actually solve the system, but just to get what the equations are. Okay? So go ahead and spend some time and talk about that one, and then we'll go over it as a group. Okay, so let's go ahead and talk about this one. Make sure that, because for whatever reason this one decided to be a clicker question, it doesn't matter what you put in, but make sure you put in something, because you won't get credit for the question. I kind of wonder why people were putting in answers for something that wasn't a clicker question in the first place, but because some people did, everybody has to now. So, okay. Or you could not do it if you don't want the points, but that's kind of up to you, I guess. So, for this one, what we want to do is we want to set up our system of equations for our two objects here. So because this is a perfectly elastic collision, the first and easiest equation to write is the one for the conservation of energy, because that just says that the kinetic energy initial state, so what I have here is the initial state, so this is the initial state, this is the final state. The kinetic energy in the initial state is equal to kinetic energy in the final state, which says that 1/2 mv1 squared is going to be equal to 1/2 mv2 squared plus 1/2 capital M v3 squared. Okay? So that's our statement of conservation of energy. Now what we need to do is we need to conserve momentum in the x direction and in the y direction. And so in order to do that, what we need to do is we need to say that for the sum of momentum in the x direction, this is going to be equal to mv1 in the initial state, and in the final state, this is going to be equal to mv2 times cosine of phi plus m, this being the capital M, mv3 cosine of theta. Okay. Now we want to sum our momenta in y. And so what that says then is that the sum of the momentum in y is going to be equal to 0, because when we look at the initial state, nothing's moving in the y direction, right? There's only moving in the x direction. And so what that says is that the sum of momentum in y is equal to 0, which is going to be equal to mv2 times sine of phi minus m capital M v3 times sine of theta. Okay? And that's it. We have our 3 equations and 3 unknowns because we don't know what any of these velocities are. Okay? And that's it. Any questions about this one? Okay. So, moving on. Now what we're going to be doing is we're going to be moving into rotational motion, and specifically we're going to be talking about the acceleration of objects when they undergo circular motion. And so there's a video that we put out that you were meant to watch for today all about this. And so basically what we want to do here is we want to think about what do Newton's first and second laws tell us about the way that objects are going to behave when we think about when they go around in a circle, essentially. So what does Newton's first law say? Who remembers what Newton's first law says? Object in motion stays in motion unless acted upon by an external force, right? And there's a key to that. It's not just an object in motion, it's an object in uniform motion. And uniform motion meaning if an object is going in a straight line, it's going to continue in a straight line forever, unless it's acted upon by an external force. So if we think about if an object goes around in a circle, can that be without any external force? No, because if it was without an external force, it would just go on forever. So there would have to be some force that acts on this object in order for it to go in a circle in the first place. And so what we can do is we can consider, here's some circle that this object here is going to go around. We could say it had some velocity associated with it. There has to be some force acting on this in order for the object to maintain this motion in a circle. And so what this question is really kind of asking you is what is the direction this force has to point. So consider an example where you have a ball and you want to get it to go around in a circular path. You have to hit it with a hammer somehow in order to get it to do that. The question here is what direction should I hit the bowling ball with a hammer in order for it to follow this circular trajectory? So take a minute to talk about that and then we'll reconvene and talk about it further. Okay, so let's talk about this one. So we have this ball it's moving in to touch the circle right here, right? And what we want to do is we want to get it to go around the circle this way. And so in order to do this, what we're going to have to do is we're going to have to hit it with this hammer in order to get it to go around this way. And it turns out that the way that we need to do that is going to be pointing straight towards the center of the circle. Now, there's a couple of different ways ways that we can think about this, I think one of the more instructive ways to do this is to think about the way that we define the acceleration. So acceleration is defined to be, a vector is going to be, in some approximation anyway, is defined to be the change in velocity divided by the change in time. Okay? So let's see if we kept hitting this around the outside to make this go around in the circle, we'd see that we had some initial velocity right here. We'd have some later velocity that looked like this. So this would be v2. Okay? So we call this v1 and v2. Now, if we wanted to find what the direction of the acceleration is going to be, what we could do is we could take the difference of these two vectors. So this delta v, by definition, is going to be v2 minus v1. Okay? Now let's see what that's going to look like. Well, if this is v2, and this is going to be v1, it's going to look a little bit more like that. So this is going to be v2, this is v1. Then the difference of these is going to give me something that points like this. So this is delta v. And between these 2 points, that tells us that this is going to be pointing towards the center of the circle. Okay? Now we could do that for various points around here. So pick any set of 2 points, and if you really wanted to do this with calculus, and take these things and move them as close as you can together, and then you'd see it points exactly towards the center of the circle. So that's one way that we could think about this from the perspective of the acceleration. So as this is going around the circle, the acceleration has to point towards the center of the circle. But that doesn't quite get us to the force. So in order to get us to the force from this perspective, what we need to do is we need to say that from Newton's second law, the sum of the forces is going to be equal to the mass times the acceleration. Okay? Now, if we think about coordinate systems such that going around the circle is one coordinate, this has some constant velocity. It's not accelerating going around the circle this way, right? Because the tangential velocity at every point is going to be constant in this example. And so the only direction you could have an acceleration is towards the center of the circle, because that's the direction that's perpendicular to tangent to the circle. And so that would tell us in another way that our acceleration is towards the center. And then the force is going to be the same direction as the acceleration, right? Okay, any questions about this? Okay, so let's move on to the next one. All right, so now what we want to do is use this information that I just kind of laid out for you. It's a little bit hard to see, but there are these two red dots. There's a red dot at north and a red dot at east. And what I'd like you to do is to draw this on your paper and then draw what the direction of the acceleration is for an object that's going around this circle. Okay, take a couple of minutes to do that. We already kind of know what the answer is going to be. A little bit. A little bit, yeah. Okay, so let's go ahead and talk about this one. So we have these 2 points where we want to find the acceleration, and like I said, I kind of gave you what the answer was in the way that I described the answer to the last one. But it's worthwhile thinking about it anyway. So if I'm at this point here, how should the acceleration point? Straight down. How about here? To the left, okay? And any point on the circle, we're going to have an acceleration that points towards the center if we're moving around with some constant velocity. There are cases where you don't have a constant velocity, and this could be a little bit different. Okay? All right, so let's move on to the next one. So this one says a car rounds a curve while maintaining a constant speed. Is there a net force on the car as it rounds a curve? And we want to think about why that might or might not be the case. Okay, so let's talk about this one. So in this example, we have this car that's rounding this curve, and we want to think about whether there's a force acting on it or not. Well, we can kind of do this by what's called a proof by contradiction. So you make some assumptions, and if the assumptions end up being not true, then your original assumption was incorrect. And so if something's going to go around in a circle, well, let me see, how do I want to frame this? So if something has some constant velocity and there's no force acting on it, what's going to happen with it? What would Newton say about an object that has some constant velocity pointing in some direction, no force acts on it? It just keeps going forever, right? Now if we look at this clearly isn't just going forever because it's going to bend around this curve, right? And so that tells us there needs to be some kind of force to redirect this so that it doesn't go on forever, okay? So now what we want to do is we want to think about for this case, what is the direction of the force in order to make it go around in the circle? So go ahead and talk about this one. Okay, so let's talk about this one. So we want to consider what the direction of the force of friction is going to be in order to keep this going around in this circle. Now, the force of friction is actually going to be the force that's keeping this going in the circle. It's not slowing down its motion like you might think, because you could have a situation where you have a component of friction that's tangent to the circle, but this is the force of friction that's keeping it going around the circle. And so that tells us that this should be pointing towards the center of the circle. Okay, so this should be E. Okay, so now what we want to do is we want to do some calculations with this. And so there's one more piece that I need to lay out here, and that's what is the acceleration when you're going around some circle. So if I have some radius of this circle and I'm moving with some velocity tangent to the circle with some velocity v, then the acceleration that we call this the centripetal acceleration, a sub c, is going to be equal to v squared divided by r. Okay? So the utility of this is when you undergo circular motion, you can plug this acceleration into the right-hand side of Newton's second law. So we say the sum of the forces is equal to the mass times acceleration, and this is the component of the acceleration in that points into the center of the circle with the way that I have this defined here. Okay, so go ahead and take a couple of minutes to talk about the one that we have here, and then we'll move on. Okay, so this one was pretty straightforward, just using Newton's second law here in order to find what the force is going to be, because we know what the radius is, the mass, and the velocity. And so what that says then is that this force F is just going to be equal to mv squared over r. And you just need to convert your miles per hour to meters per second, and when you evaluate this, you end up finding something that's approximately 9,200 newtons. Okay? Not too bad. All right, so let's move on to the next one. So now we're looking at a situation that's going to be a little bit more complicated because there are more forces that can act on this one. Because now instead of having just a horizontal circle, we have a vertical circle. And so what we want to do is we want to think about this in terms of a free body diagram and everything that we did earlier in the semester when we were talking about forces when we needed free body diagrams, and that'll help you do this one. Okay, so go ahead and talk about this one, and then we'll come back and talk about it as a group. Okay, so let's go ahead and talk about this one, and then I think that's going to be it for today because we don't really have time for another one. Unless you guys really want to do another one, then we can. Okay, so let's go ahead and get through this one quickly, and then that'll be it for this week, actually. We don't have class on Thursday. So, okay, first thing that we want to do with this problem is to draw a free body diagram. So for this bucket, when we draw the free body diagram, we're going to have two forces acting on it. The first force is going to be the force of gravity. This is going to be mg pointing down. The second force is going to be tension. Tension is also pointing down. Now, when we have our free body diagram, that's going to lead us into wanting to use Newton's second law. But before I do that, I'm also going to draw some coordinate system. So I'm going to say that this is going to be the positive direction. So Newton's second law says that the sum of the forces is going to be equal to the mass times the acceleration. This is a acceleration vector, not a mass vector. So when I sum my forces here, they're both in the same direction as the direction I say is positive here. This is T plus mg is going to be equal to ma. Now I want to solve for the tension. And so in order to solve for the tension, I move the gravity to the other side. This is going to be T is going to be equal to m times a minus g. But we know something about the acceleration in this case because this is going around in a circle. This acceleration is the centripetal acceleration, so this says T is going to be equal to m v squared over r minus g. And now when you take this equation and you plug the numbers into this, you end up seeing that this is going to be 13 newtons, about. Okay? So that's going to be it for us this week. If you have any questions, come up and ask me, but I'll see you guys next Tuesday. Yes, turn in your homework at the front. Yeah.
The email I sent you so I can get the credit.
Right.
I even asked my peers if they had the same as me.
Yeah.
They had the same, but I got it wrong.
Was this a matter of like the index?
It is.
Like you're trying to do something with like an m sub p or something? Yeah, I can give you credit for that. That's something we knew about. I think Professor Shepard sent out an email to her students, but maybe not my students. I don't know.
Yeah, you didn't reply to me, so I sent another email to Shepard. He told me to talk with you in class.
Okay, yeah, that's fine. That's fine. I'll fix that. It's kind of unfortunate in a way that I had my internet browser up before I was watching Twitch before class, and that comes up, and then you guys probably think, oh, he's just watching Twitch over here. I actually didn't. But okay, let's see. This is this one, and WebAssign.
In most of my classes, I have problems with that.
Yeah, it's not ideal.